Okay, everybody, chapter 8. I don't know about you, but I'm really tired today, so I'm going to try not to yawn a bunch of times like I did the other day, but let's see if we can get through this. Confidence intervals for population mean with the population standard deviation known. So we're going to construct and interpret confidence intervals for a population mean when the population standard deviation is known. We're going to find critical values for confidence intervals. We're going to describe the relationship between the confidence level and the margin of error. We're going to find the sample size necessary to obtain a confidence interval of a given width. And then finally, distinguish between confidence and probability. Okay, here we go. First, we're constructing and interpreting confidence intervals for a population mean when the population standard deviation is known. So we're going to look at a random sample of 100 fourth graders. Is selected to take part in a new experimental approach to teach reading. At the end of the program, the students are given a standardized reading test. On the basis of the past results, it's known that the scores on this test have a population standard deviation of 15. So the sample mean score for the 100 students, when they did the 100 students and they pulled the simple random sample, that sample mean was 67.30. Now the administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. So the best estimate for the population mean is the sample mean, because the sample mean is a point estimate. It's a single number. So it's very unlikely, though, that the mean is 67.30, exactly equal to the population mean. So in order to be estimate to be useful, we must describe how likely it is to be. So for example, if we think we could be off by 10 points, we would say that mu would be greater than 57.3 or less than 77.3, which would be written as 67.3. You might hear people say give or take 10 or plus or minus 10. But a lot of times people will just use the language give or take 10. Okay, so let's take a look at, let me see if I can get rid of a little bit of that glare. There we go. Let's take a look at plus or minus. The plus or minus part of this is your margin of error. This part right here is your margin of error. Alrighty, so suppose we want to be 95% confident in our interval, and it's a very common confident interval to choose. So we need to determine how large to make the margin of error so that the interval is likely to contain the population mean. So to do this, we use the sampling distribution of X bar, which is the mean. Because the sample size is large, greater than 30, the central limit theorem tells us that the sampling distribution of X bar, or the mean, is approximately mu, and the standard deviation would be the standard deviation divided by the square root of how many are in our sample. So again, we have our sampling distribution, and our standard deviation will be our standard deviation divided by how many are in our sample. Now, our mean value is still going to be the same as the mean value here. So this is our starting point, and then we're going to have a margin of error to it. So for teaching the reading example, the standard error is, okay, so we know that the mean is 67.3, the standard deviation is 15, n is 100. So if we go over here and we use the formula and we put in the standard deviation divided by the square root of n, that would be 15 over the square root of 100, and we get 1.5. Now, to construct a 95 confidence interval for mu, we begin with a normal curve and find the z-scores bound by the middle 95% area of the curve. Now, 95% interval is a common interval, so we know that the z-score is negative 1.96 or 1.96. You might say, well, I didn't know that. Well, probably because we have been learning so much in a short period of time, but these are two common ones that you will use that match up with the 95% confidence interval. So the value of 1.96 is called a critical value. To obtain the margin of error, we multiply the critical value by the standard error. And this is our standard error. So margin of error equals our critical value times our standard error. So 1.96 times 1.5, and that'll be 2.94. That's our margin of error, so we're going to take our mean value plus or minus, give or take, 2.94, so that will give us 67 plus or minus 2.94, which gives us the interval of 64.36 to 70.24, but not including. Okay, so what are we doing here? When we're looking at the confidence interval of 100 fourth graders using a new approach teaching, 95% confidence interval for the mean score was constructed. What does that mean? The 95 confidence interval means that the confidence interval measures the success rate of the method used to construct the confidence interval. In other words, if we were to draw all these samples, okay, these are all the samples that we drew by pulling out. If we were to draw many samples and use one to construct a confidence interval, then in the long run, the percentage of confidence intervals that cover the true value of mu would be equal to the confidence interval. So you see this line coming down here and how it hits almost all of them. This one, maybe not a little. This is one that it doesn't really hit. Keep coming on down, 2. Keep coming on down, 3. Keep coming on down, 4. Keep coming on down. Okay, so the next one was probably up here, which was the iffy one. So this would be our 5th one. So you see 5 of them really weren't covered by the line coming straight down, which means the other 95 are. So that's how you get that 95% confidence interval. Now, a point estimate is a single number that's used to estimate the value of the unknown parameter. The confidence interval is an interval that is used to estimate the value of a parameter. The confidence level is a percentage between 0 and 100% that measures the success rate of the method used to construct the confidence interval. And the margin of error is computed by multiplying again the critical value by the standard error. And that's what you plus or minus the margin of error. Find critical values for confidence intervals. Okay, so now we have a 95%. I've already told you is one of the most commonly used confidence intervals. When you read research, you will see it will say directly in there had a 95% confidence interval of, and sometimes we want to construct a confidence interval though of a different level. And we can construct a confidence interval with any confidence level between 0 and 100 by finding the appropriate critical value for that level. Now, critical values for several common confidence levels are given in the bottom row. So these are the ones that are common. You can have a 20% confidence interval, 50%, 80%, 90%, 99, 95, 98, 99, 99.5, 99.8, 99.9. Would you ever really want to say 100% confidence level? As a researcher, I would say no, you really wouldn't, because you're not giving yourself any type of error leeway. So a large sample has a mean of 7.1 and a standard deviation of the standard error of standard deviation over the square root of n. That's 2.3. Now, we're going to construct a 90% confidence interval over the population mean. So 90%, going back to that chart we just looked at, is 1.65 would be our Z value. So we're going to take our critical number, which is 1.65, times our standard error, which is 2.3, and we will get 3.8. So that means for a 90% confidence interval, we're going to take our mean value, which is 7.1, give or take, plus or minus 3.8. So when I add that and subtract it, I will get the interval of 3.3 to 10.9, not inclusive. So looking at the Z notation, sometimes we need to find a critical value for a confidence level that is not given in a table. And to do this, we need to learn a notation for the Z-score with a given area to its right. So the notation of Z alpha refers to the Z-score with an area to its right. The notation Z alpha over 2 refers to the Z-score with an area of alpha over 2 to its right. Now, if you take the middle of this area and you say the entire area is 1, and you're going to subtract whatever this area is left, we'll say alpha, then what would be left between this and this over here is going to be alpha divided by 2. So, we're going to take a look at negative Z alpha over 2 and Z alpha over 2. That area in between will be 1 minus alpha. These Z-scores can be used by using a table in A2 or using your calculator. Now let's take a look, finding the critical value of ZA over 2 for a 92% confidence level. 92% confidence level, you would have 92 here. That leaves 8%, so there'll be 4% here and 4% here. So the critical value would be Z at 0.04, Z 400ths. So since the area to the right of it is 0.04, the area to the left of it, all of this area to the left of it would be 0.96. Now when we use our table or technology, we know that we have 0.96 and we're looking at this, so we want to know what that value is, that Z value, and we will see that we have 1.75. 1.75. So if we want to know what our area is under this curve, and we're looking for the Z value for what this would be right here, then we find this value because we added these two together and we get 1.75. All right, now assumptions. A method described for a confidence interval requires us to assume that the population standard deviation, which is little sigma, is usually not known. So in practice, it is not known. So we make this assumption because it allows us to use a familiar normal distribution when we learn how to construct confidence intervals when little sigma is known in the next section. So for now, other assumptions that we use for the method described here for constructing a confidence interval are as follow. We are assuming that we have a simple random sample. So when we do this, we're already saying, people check this out, it's a simple random sample. And we are saying that the sample size is either greater than 30 or we know that the population is approximately normal, one of the two. So if we look at a machine that fills cereal boxes and it's supposed to put 20 ounces of cereal in each box, an SRS of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It is known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounce. So construct a 90% confidence interval. Well, first we have to check the assumptions. When we check the assumptions, we see that we have an SRS, they tell us that, and that the population is known to be approximately normal. So I go to my 90% value, my confidence interval value, and I get 1.645 confidence level. So I'm going to take that standard deviation here, divide it by my sample, which is the square root of, well, divided by the square root of my sample, which is 6, and I will get 0.08165. And what am I going to do with that? I'm going to take that z value of 1.65 or 0.165, multiply it by that value, and I will get 0.1343. Now, the 90% confidence interval that I'm developing with that is plus or minus 1.343. So I have my 25.25, and I'm adding and subtracting this value of 0.1343. Look at this error again. We're going to cross that out. Okay, so this should be 0 here. Okay. So now when we add or subtract right here, give or take, then we're going to get 20.12 and 20.38. So the 90% confident that we will find the mean weight, T, mu, is between 20.12 and 20.38. All right, now, you can find the confidence interval on your TI-84 by using your Z interval command. Constructs the confidence interval when the population and standard deviation is known. This command is accessed by pressing Stat, highlighting the test menu. So tests are over here. And the summary statistics are given Stats option. Should be selected for the input option. So when you're over here and you get the Z interval, then you're going to hit the Stats option. So looking at this same example that we talked about a moment ago, we're going to press Stat, highlight the test, select the Z interval, and then select Stats as the input option. Enter our 0.2 in the standard deviation field, our 20.25 in our mean field, our 6 for our number in our sample or our N, and 0.9 for our C level confidence interval, and then select calculate. And when we do that, we will get the confidence interval of 20.12 to 20.38. Objective 3. Describe the relationship between the confidence level and the margin of error. If we want to be more confident that our interval contains a true value, we have to increase the critical value, which will increase our margin of error. But there's a trade-off. Would we rather have a higher level of confidence than a lower level, or would we also rather have a smaller margin of error than a larger one? This can be tricky, because if you say, well, I'm 70% confidence that something is going to happen, then 70% confidence really doesn't sound that impressive. If you say 95% confident, I mean 95 out of 100, this is a pretty good compromise between the reliability and the margin of error for a lot of purposes. It's a very common one to use. But if you say 99.7, then the confidence interval, you're going to have a much larger area here that you're meeting, and to be 95% confident, you're going to have to say, you know, I'm 95% confident that a lot of people are going to, that this many people in this group are going to be above 4 foot and below 7 foot tall, you know, something like that. So you want to kind of make sure that when you're using confidence intervals, it sounds pretty impressive, but it's also reliable, that you have done your homework and that you have a pretty good interval. All right, measuring the success rate of the method. So in the diagram represents 100 different 95% confidence intervals. When we construct a confidence interval with 95%, we're looking at one of these confidence intervals. We don't get to see any other confidence intervals, nor do we get to see the vertical line that indicates where the true value is. We cannot be sure whether we got one of the confidence intervals that covers mu or whether we were unlucky and to get one of the 5 that does not cover mu. You just saying, I'm 95% confident that I'm correct. What we do know is that our confidence interval was constructed by a method that is successful 95% of the time. And the confidence level describes the success rate of the method used to construct a confidence interval, not the success of any particular interval. Okay, let's look at finding the sample size necessary to obtain a confidence interval of a given width. All right, so we can make our margin of error smaller if we're willing to reduce our confidence level, but we can also reduce the margin of error by increasing the sample size. So if we let M represent the margin of error, then we will take our, remember this number is for our confidence interval, our z-score, that value of standard deviation divided by the square root of n. If you make this value, your sample value, larger, then you can make your margin of error smaller. So which represents the minimum sample size needed to achieve the desired margin of error? If the value of n given by the formula is not a whole number, round it up to the nearest whole number. By rounding up, we can be sure that the margin of error is no greater than the desired value of m. So scientists want to estimate the mean weight of mice after they have been fed a special diet. From previous studies, it is known that the weight is normally distributed with a standard deviation of 3 grams. How many mice must be weighed so that 95% confidence interval will have a margin of 0.5 grams? So we're looking for how many we would want to have. So since we want a 95% confidence interval, we'll use the value 1.96, which we already know. We also will use our standard deviation of 3 that was given to us and our margin of error, which is 0.5. Once we put these values in, we will have 1.95 times our 3 all over 0.5, and then we're going to square that. So we get 138.3, but we're going to round that up to 139. Okay, so we must weigh 139 mice in order to retain the confidence interval with a margin of 0.5 grams. Now you might be thinking, well, why don't I round down? Because remember, you want to make sure that you're including this portion of a mouse, let's say, this portion in our confidence interval, because that's the number that we got. So if you round down, it's like you're not counting that portion. If you round up, then you definitely have it in your interval. Now let's distinguish between confidence and probability. Suppose that 90% confidence interval for the mean weight of cereal boxes was computed to be 20.12 to 20.38, not inclusive. It is tempting to say that the probability is 90% that mu is between 20.12 and 20.38. The term probability refers to random events, which can come out differently when experiments are repeated. So the numbers 20.12 and 20.38 are fixed. They're not random. The population mean is also fixed, even if we don't know how precise the value is. The population mean weight is either between 20.12 and 20.38, or it is not. Therefore, we say we have 90% confidence that the population mean is in this interval. On the other hand, let's say we're discussing a method used to construct the 90% confidence interval. This method will succeed in covering the population mean 90% of the time and fail the other 10% of the time. Therefore, it's correct to say that a method for constructing the 90% confidence interval has a probability 90% of covering the population mean. Tricky vocabulary. All right, so from this lesson, you should know how to construct and interpret confidence intervals for a population mean when a population standard is known, how to find critical values for confidence intervals, how to describe the relationship between the confidence level and the margin of error, how to find the sample size necessary to obtain a confidence interval of a given width, and the difference between confidence and probability. Okay, so that's it for 8.1. I will talk to you again for 8.2.